Okay, hello everyone. In this video, we are going to solve this generate parenthesis problem, and so this is what we are given. We are given an integer that is our input, and we are asked to generate all the combination of well-formed parentheses. So we are given an input, and we are asked to generate all possible combination of well-formed parentheses. So from here, what I can already conclude is, for us to return all the valid well-formed parentheses, we need to first generate a state tree which has all the combinations. Even if it's invalid, we'll have everything. We have valid solution, we'll have invalid solution. Basically, we will generate all the possible scenarios of later. When we have all the solution, we have all the possible solutions, then what we can do is basically we can pick out only the well-formed parentheses and ignore every other invalid options. So this to me sounds like backtracking problem. So what is backtracking? If a problem needs all the possible solutions, even if that is valid or invalid, meaning if we need to generate all possible scenarios, then we do backtracking at that. And this to generate all possible solution, what we can do is we can use recursive programming. So if we can use this to feels like we can solve this problem. And so let's see how we can do it. So we need to write a function that's recursive function recursive, right? We need to write a function that's recursive, and we are given this number n, and at a given moment. So let's say if we start from here, right? We can start by adding opening parenthesis. Then at the second time, we have the option either to use a closing bracket or to open a okay, let's make it simple. We can either again add another opening bracket like this and make it like 2 opening bracket, or we have option to close this, right? And add this again when n equals to 3. Let's say when n equals to 3, again here we again have an option either to add one more opening bracket and not have any closing bracket, or at this time we can maybe open one more opening bracket like this. But what we cannot do is we cannot have like this. We cannot have an option like this where we have only one opening bracket but we have 2 closing bracket. This is simply invalid. So if we define a recursive function that generates our answer, which is all possible valid in a parenthesis, then what we want to do is simply from this example, right? Here we have n equals to 3, so we will create this opening parenthesis. Then we have another option to add one more opening parenthesis, and now if we are at this point, we cannot add another opening parenthesis at all, because this violates the rule that we can now if we want to make this valid, we need 4 more closing bracket, right? And if we add 4 more closing bracket, then this becomes n equals to 4. So at this point we should start closing out our first bracket. So we should start closing out like this. So if we just observe this example, what we can do is we can say, let's say we need a function to add a parenthesis, this is right, and then let's say we'll start from add opening parenthesis, and then we'll do add closing parenthesis, right? This is what we can start out with. And since this is recursive, what we also know is for every recursive function we need a base case to at least terminate it. Otherwise this is going to be an infinite loop. So what's the base case here? For n equals to 3, we have a valid solution of total 1 2 3 4 5 6, and then same 6, and then the same size of 6, because if we can use 3 opening bracket, we have to have 3 closing bracket for the valid solution. So all the time our solution is going to be n times 2. And if our solution, the current possible case, for example, if the current string that we are calculating, if that size, then we know it's valid. We need to terminate at this case. So we will store all our result in the result array. So result dot push current parenthesis, let's say current string in this case, and yeah, current string in this case, and we'll simply return from here. We'll not do anything else. This is our base case. And so if we already need current string and then a result, why don't we just add it in our recursive as well? So current string and then results. Okay, so we are done with our base case, and now we'll are left to implement the actual logic for our problem solution. So here we either have to add opening bracket or we have to add a closing bracket, and so we can only add a opening bracket up to 3 times, right? Up to 3 times in this solution, and here up to 1 time. So if our current opening, so or we can say or opening count, right? Opening count is greater than 0, means if opening will basically reduce 1 every time we process the we'll add the opening bracket. And so this is how we can do it. So we'll recursively call it recursive, and then we'll pass n. Then we also know our current string needs to be there, then we'll also pass the result. And let's say current string, if we add opening bracket to a current string, then we'll need to reduce the opening count, right? So then opening count -1. So we need to reduce the opening count since we already used it in this current iteration. So this is what we'll do for now, right? And in order to use this opening count, we will also need to add this here, opening count. So this is that, and maybe yes, so that's that. And for the closing count, how are we going to do it? How are we going to write the logic for closing count? This time you use the opening bracket for 3 times. You can also use the closing bracket for 3 times, but if you have opening bracket 2 times, you have to close it for 2 times. If the opening bracket is now only 1 time left, then you have to close it for 1 time. So meaning if your closing count is greater than the opening count, so that means if you already, so let's say you've used your first 3 opening count, this means that your current string is like this, right? If your current string is like this, then this means your opening count is now what? Opening count is now almost, it's 0, right? So first time it will be 3, 2, 1, and now it's going to be 0. And here what you are going to see, so this means that the closing count, as long as you have more closing count left than your opening count, you're going to use your closing count. So that means recursive and current string, now you add the closing, and then you pass the results as it is, and then you say you pass the opening count, now the closing count -1, right? And you have to pass the closing count as well, closing count, right? And at the end, when this executes, you have to return the result. So let's say you are returning a results, right? Return result, and now you simply call this function. So here what it is happening, right? So since we know we need to generate all the combination, this rings a bell that it's a backtracking problem. In the backtracking, you have 2 solid foundation. You need to generate all possible cases, and the way you can solve this generating all possible cases, that is a bigger problem, is using a recursive problem, basically breaking down a bigger problem into a smaller sub problems. And this is where we used recursive. And for if you are using recursive function, you need to have a base case. And here all the valid solutions as n into 2 times of length, because if you use an opening bracket, you have to have a closing bracket. So this is our base case. We are building up a string. We are either adding a opening bracket or we are closing or adding a closing bracket for our current string, right? And so anytime you add a current opening bracket, you reduce the opening count. Now let's also pass the closing count here, and same for the closing count. This is fairly simple. We are till the given option, that is n equals to 3, and once it reaches 0, then we'll not add any more opening bracket. Then we'll work on towards reducing the closing bracket, and this will be 0 by the time we add all our valid possible cases. And the closing count, we reduce it from here. And so once we will only be adding the closing bracket as long as we have the option to do it, and we'll have to return the result. And so let's see, now all we need to do is simply call this recursive function, and let's see, we can call the recursive n equals to n, and we are only given n. Then current string, we have to pass it the empty string. Then maybe we'll define a result like this. And then what else? Opening count. How many opening counts do we have in the beginning? We have 3 opening counts, that is n, and then 3 closing counts. And what else? So that 1 2 3 4 5, so total of 5 parameter. And then this is what is going to be written at the end. So maybe we'll return that. So let's see if it works. Recursive is not defined, so maybe I misspelled it. Okay, nice. And if I submit it, let's see if it works. Nice, it worked. So this is how it can be solved. So anytime the main key takeaway is, if you need to generate all possible cases, then that will ring a bell that you have to use a backtracking algorithm. And backtracking algorithm is basically steps onto 2 foundation. It has only two foundation, that is, you need to generate all possible case, and the way you're generating this possible case is basically using recursiveness. So and if you are going to use recursiveness, you have to have a base case, which